Great, thank you. So I'll get to the outline in a few slides, but first I would like to motivate why are we using diffusion MRI, and for that we should consider the different length scales. So on the one side you have your NMR signal, which comes from the molecular level, which are nanometers, and you have your image, which are millimeters. And what you really are interested in, for instance, in the human brain, is the cellular scale, which is the intermediate scale between the molecular level and the imaging level. We call it the mesoscopic scale or the intermediate scale, and this is really the scale that you would like to look at, because this is where your pathology will start. This is where you will have demyelination or axonal beating. So this is where you would like to look. But as I said before, with MRI you look at millimeters, and really you would like to get down to about 1,000 times lower, to the micron scale. And this is an electron microscope of the hippocampus of I think of a mouse. And luckily there's diffusion, because with a diffusion MRI experiment you look at the random motion of a water molecule over a few milliseconds. And the time scale is really important here, because you have a few milliseconds during which your water molecules will diffuse over a few microns. And over those few microns, your water molecules will probe the microstructure. The diffusion will be sensitive to the presence of cell walls. It will slow down maybe inside because of organelles and so on. So you could argue that diffusion really can act as an in vivo microscope. And I think the most illustrative example of how sensitive diffusion MRI is stroke. It's first been observed in 1990 by Mosley and colleagues in cats. Here I'm showing it in humans, so you can see that if you look at conventional T2, you see multiple locations of T2 lesions, but really it's on the diffusion where clearly the ischemic lesion lights up minutes after the onset of the ischemic event. And this is really what started the field of diffusion MRI. This is what's still been used in clinic daily. But what's then the problem? So the disclaimer is that while diffusion is extremely sensitive, it will be sensitive to changes through development, aging, lots of different types of pathologies. I mentioned ischemia, but there's many more. The problem is its specificity. As you saw, the signal itself is still coming from the entire voxel. So you cannot be really sensitive to what exactly is changing at the level of the microstructure. And the most notorious example, again, is the diffusion drop as observed in stroke. There's been many theories proposed, and until today, there's no consensus on what exactly is causing the diffusion drop in stroke, and I'll get to this later in the presentation. And then here, this is the parameter space of diffusion MRI. It's already shown by Jennifer earlier. So how do you encode the diffusion signal? So the B value, it's really consisting of two terms. So first of all, you have the diffusion gradient you can vary, which is encoded by the Q vector. But you can also vary the diffusion time, and you can see that those two are independent metrics. So in a way, you could say that while we typically say that we measure the diffusion as a function of the B value, you should consider that you either vary the gradient or you vary the diffusion time. So you could call it QT MRI if you wish. So this brings me to the outline of my talk. So most in this lecture, I will talk about how diffusion modeling or probing the microstructure has been done by varying Q or the gradient. Flavio already spoke a lot about DSI and Q-ball, so I will focus on DTI and DKI. These are two very popular techniques used in clinic. They have a lot of signal because the diffusion signal is relatively low. Then I'll talk about how you can use the same signal for microstructural models. And then at the very end, I will talk a little bit how you can, by varying the diffusion time, also probe the microstructure and get direct access to microstructural length scales. So first DTI and DKI. So this is a little bit repetitive, but maybe it's good. DTI, I'm showing here the diffusion signal as measured in the white matter. So what diffusion tensor imaging does is, if this is a log scale as a function of the B value, so what it does, it's fitting a linear function to the log of the signal. So this is the same as fitting an exponential function to the signal. If you have an isotropic medium, you have to do this only in one direction. However, as been shown before, for instance, white matter is highly anisotropic, so you would need to reconstruct a diffusion tensor. So for this, you need to acquire at least 6 or more directions. So then you can make the diffusion tensor, which you can represent by a diffusion ellipsoid, already mentioned before. You can diagonalize the tensor, which will give you your eigenvalues and your eigenvectors. By convention, the first eigenvalue, lambda 1, is the largest, and the corresponding eigenvector points towards your primary direction of diffusion. The metrics you derive are the mean, axial, radial diffusivity, and the FA. I'm showing parametric maps here. It's maybe interesting to point out that the MD is very homogeneous. There's no contrast between gray and white matter, whereas if you look at the axial, the radial, and especially the FA, you can see that the FA really lights up in highly anisotropic regions. So as mentioned before, what's the limitation? So I would not say that DTI assumes the diffusion to be Gaussian. I think DTI only samples the Gaussian part of the diffusion signal, which you can clearly see here. Here the signal really decays exponentially, but you can also see that if you go up to higher B values, that it starts deviating from the exponential decay. So with DTI, you really cannot probe more than the Gaussian properties of your diffusion signal, and you only should apply it to low B values. And one method that goes up to higher B values and that probes this non-Gaussian signal properties is diffusion kurtosis imaging. So instead of a linear function of the log, you now fit a quadratic function of the log. And because of this, you can probe this curvature of the signal. Again, if you do, and this gives you not only the diffusion tensor, but also your kurtosis here. A kurtosis of 0 would mean it's a Gaussian system. Your kurtosis is 0. In vivo, typically your kurtosis is positive. And again, if you do this in an isotropic medium, one direction is sufficient. If you did this in an anisotropic medium, you have to go to the tensor, which now is second-order tensor, a fourth-order tensor. So you would need to have at least 15 independent directions. One caveat, again, same for DTI, you go up to B1000. For DKI, you cannot go up much higher. The rule of thumb is B should be smaller than 3 divided by dk. So D is roughly 1 micrometer square per millisecond. K is on the order of 1. So that implies that the B value should be smaller than 3000. If you would do this ex vivo, you know that your diffusion coefficient may be lower, so then you can go up to slightly higher B values. Again, you can make parametric maps. You have the same DTI maps, but now you can also have the mean kurtosis, axial and radial. And now you see nicely that the mean kurtosis is actually different in gray versus white matter. I put 3 dots there because you can come up with your own metric, and I made these maps with this software if you're interested. So just to summarize, DTI you need 6 directions, DKI you need at least 15 at an additional B shell. You can go up to slightly higher B values. DTI gives you the diffusion tensor, DKI in addition your kurtosis tensor. It will probe the non-Gaussian parts, and I'm not showing an example here, but because of that you can actually resolve fiber crossings, whereas with DTI you cannot. And both of those have been used quite a lot for brain applications. So the typical standard protocol is 2 B values along 30 directions. Recently, you can do this in 5 minutes because of parallel imaging and multiband. And recently it has been proposed when you assume axial symmetry, you need only 9 directions, and then you can do it in 1 to 2 minutes. And it has been applied to a lot of different brain pathologies. I'm not going to go over them, but you can look up these references. There's a lot of other higher order methods. DKI is just one example, and I think Flavio also nicely illustrated there's actually hundreds of choices. And this has, I took this from a poster from Thijs Dollander, who once presented it at the ISMRM study group. So it may look a little bit overwhelming. There's so many models. However, it's important to know that there's really two types of models here. On the one hand, you have biophysical models. On the other hand, you have signal models or representations. And with a biophysical model, you really have the microstructure in mind and you try to mimic the microstructure. Whereas with a signal model or a mathematical model, you have your function and you try to fit a mathematical function without having the reality in front of you. You can see that those two models are inherently very different. Biophysical models, they are developed for a given tissue type. You may develop them for the gray matter, for the white matter, could be for a tumor, and you can see that you cannot use the tumor for maybe the white matter or vice versa. They are by design very specific because you have the microstructure that you'd like to mimic, but you also need to validate your assumption that you make in that model. On the other hand, you have representations. They are model independent, and they are not dependent on the tissue. And I showed one example of a signal representation, which was a cumulant expansion, which is expanding the log of the signal in functions of BD. First order is DTI, second order is DKI. There's many more. I'm not going to go over them. There's a bi-exponential, stretch exponential. And just to illustrate, this is the same signal in the brain white matter as a function of B. And you can see that those three signal representations, the cumulants, bi-exponential, and stress exponential, they fit the signal equally well. So then the next part I will talk about is about brain microstructural modeling. So the model that everyone has been using in the brain so far relies on one main assumption. And the assumption is that axons can be modeled as impermeable cylinders or sticks. And often the dendrites are also included, and then they call them neurites. And you could call this the standard model because you can see it's been used by everyone so far modeling the diffusion in the brain. So what is the standard model consisting of? There's at least two compartments. There's the intraaxonal space and the extraaxonal space. The intraaxonal space in this case is a collection of cylinders or sticks. Each cylinder is characterized by an axonal diffusivity, potentially an axon diameter, and they are oriented according to a certain fiber ODF, as also explained by Flavio. Then there's the extraaxonal space, which typically is modeled by a Gaussian anisotropic medium. So there you have the axial extraaxonal and the radial extraaxonal diffusivity. Obviously, you have the two compartments have a certain fraction, so it's been called the axonal water fraction. It's also been called the neurite density. It's the volume, it's the water fraction of the inside over the inside plus outside. One important thing to note here is that the myelin is not included in this fraction. That is because with diffusion MRI, your echo time is typically very long, and myelin has a short T2. And then potentially you also have other compartments such as CSF or maybe still water fraction. So why would we want to do all the trouble to get to these parameters? Well, we think that you have increased specificity. For instance, the axonal diffusivity is a marker for acute axonal injury if you have beating. Your fiber ODF could be interesting to look at the dispersion, for instance, in pruning, could be used as an input for fiber tracking, maybe for pre-surgical planning. Your extraaxonal diffusivities could be sensitive to inflammation or demyelination. Your neurite density or axonal water fraction could point towards axonal loss in neurodegeneration. Your CSF fraction may tell you about atrophy, edema. So you can see that really it would be very interesting if we can probe directly those pathological processes rather than the empirical diffusion signal. So then how can we estimate those model parameters? And I will focus here on how you can do this on clinical scanners, on human brains in vivo, maybe even with connectome scanners. And the first thing to note is that unfortunately the axon diameter we cannot probe on a clinical scanner maybe not even on a connectome scanner. This has been shown now by multiple groups. The diffusion signal, unfortunately, is not sensitive to the axon diameter unless you go up to very strong gradients or very short diffusion times. So in this model, we will always assume that the axons are sticks. They have a 0 radius. So how can we model this? Typically, this is a nonlinear model, and this is work done by Liana Jelescu. So what she did was she tried to fit all these parameters whereby the ODF was modeled by a Watson distribution. And she did this on the human connectome data, which is high-quality data. She looked at the posterior limb of the internal capsule. She did the nonlinear model fitting for all voxels, and these are the parameter histograms that came out for the axonal water fraction, the compartment diffusivity each. And what you can see here is that those histograms are extremely broad, which means they're uninformative, and they're bimodal. There seems to be 2 possible solutions here. So this is a bit unfortunate. So it means that the diffusion signal, as we measure it with standard Stejskal-Tanner monopolar gradients, is degenerate. It means that there's multiple solutions, and because of the clinical diffusion MRI signal being very noisy, the outcome of this nonlinear fit is basically meaningless. So what's been done so far is to make the parameter estimation more robust. There's additional constraints put on the used to extract the model parameters. And in what's next is I will show two commonly used models and just illustrate how constraints can actually change the outcome of your model fitting. So the first one is NODI, neurite orientation and density imaging. It's been very popular. The constraints that are used here is that you model the fiber ODF by a Watson distribution, where you have this kappa, where kappa, higher kappa means more aligned. The second assumption is that all the compartment diffusivities are actually fixed. They're not fitted. They're fixed to a certain value, depending on whether it's adults or early development. And you have also this tortuosity constraint. So all the compartment diffusivities are fixed, and this is needed to make the fit robust. So you end up with 3 parameters. The other model that I illustrate in the next slides is white matter tract integrity from DKI. The constraints here is that you have 2 compartments, no CSF, and it's working for a single fiber bundle with a dispersion of less than 30 degrees. In this case, you can model the compartment diffusivities by tensors, and you have the axonal water fraction. And the trick here is that you can derive them analytically from diffusion kurtosis imaging metrics. And the big advantage here is that this is a linear fit, and this makes your fit robust. That being said, there's still 2 solutions, so we had to pick one where the intraaxonal is lower than the extraaxonal. So you have those 2 models with different constraints, and both of these models actually can be used on clinical data, clinical as in multiple shells, but still low B values and not a large number of directions. So we have a lot of human brain data, so we could look at, for instance, normal early development. So we compare NODI with WMTI in early development. So we had cross-sectional data between 0 and 4 years old. And this is the intracellular fraction versus axonal water fraction. This is NODI, this is WMTI. They represent the same biophysical metric. And what you can see is that NODI, first of all, has a CSF fraction, whereas WMTI does not have it. And you can see that the intracellular fraction versus axonal water fraction, luckily both they increase with development, which is what you would expect. However, you can see that quantitatively the metrics are already different. You could also look at the fiber dispersion from both models. This is the FA of the intraaxonal compartment only. So you can see that from 0 to 4 years old, NODI, the blue line, does not show a change in the FA, whereas WMTI actually shows an increase in the FA of the intraaxonal compartment. The red line is the overall FA in this case. So interestingly, you can see that NODI does not show a difference at early development, whereas WMTI does show an increase. And this is done for the genome of the corpus callosum. And so really what I wanted to say here is that you have the same data, you analyze it with a different biophysical model with different assumptions, you may end up getting different results. So really we need to have more validation, and probably we need more than just a standard monopolar diffusion signal to extract all these metrics. That being said, as I said initially, the ultimate goal of biophysical modeling is to have increased specificity. And I just would like to illustrate that this is data on acute ischemic stroke. As I said initially, diffusion MRI has been used a lot for detection of acute stroke. You have a decrease in the diffusivity as well as an increase in the kurtosis. The problem is that it's not well understood what is the cause of this effect. It has been suggested cell swelling. There may be active flow mechanisms that stop. There may be intracellular changes in the intracellular diffusion. There may be beating. So what if you would apply the modeling? So in this case, we applied WMTI. And what you can see now is that the red here is the stroke lesion, and the blue is a lesion, is the normal appearing white matter on the contralateral side. So you can actually see that there's a decrease in the intraaxonal diffusivity, slight increase in the axonal water fraction, and also changes in the extraaxonal diffusivity. So this is the same thing in a box, in a bar graph. So what you really see is that what's driving the changes here is a drop in the intraaxonal diffusivity. It drops by about 50%, and there's only minimal cell swelling. So this is actually consistent with the axonal beating as was proposed earlier by Matt Booty, and he showed it in ex vitro experiments. So if you stretch the axons, you see that there's little beats being created inside the axons, and this really will effectively bring down your intraaxonal diffusivity. So this is one illustration how biophysical modeling can actually inform you about what is going on in terms of the microstructural pathology. One other example here is how you could model neurodegeneration. So you have demyelination, for instance. This is a Monte Carlo simulation. You could have axonal loss. This is a packing of axons, a simulation of a packing of axons. Or you could combine both. You have demyelination and axonal loss. Now, if you have your model parameters, so this here is your tortuosity, which is described by your extraaxonal axial over extraaxonal radial as a function of your axonal water fraction, which was same as neurite density. So what you could see now nicely is that if you start here, axonal loss will change your axonal water fraction, but not really your tortuosity, whereas demyelination will change your tortuosity, but not your axonal water fraction. And this is quite interesting because if you would do the same with DTI, you can actually see that you cannot really disentangle those two effects as well as with those modeling parameters. And again, you could apply this on human data. This is done here for the splenium of the corpus callosum. We compared normal controls with MCI, mild cognitive impairment, and AD. And what you can see is and this is for the splenium of the corpus callosum, what you can see is that when you go from normal controls to MCI, the shift is mainly along the demyelination axis, whereas from MCI into AD, there's also a shift in axonal loss. So this would imply that in the white matter in Alzheimer's pathology, converting from MCI in AD is really characterized by axonal loss on top of demyelination. So these are just two examples that actually illustrate the power of biophysical modeling. That being said, it's still quite hard because we have those constraints, and those constraints need to be further validated. So as a last part of my talk, I will briefly talk about time-dependent diffusion. It's been said before, Jennifer nicely showed how you can either use oscillating gradients or stimulated echo to vary the diffusion time. And why would you like to do that? Because we do know that the diffusion coefficient depends on the diffusion time. If you increase the diffusion time, your water molecules are allowed to diffuse further in the microstructure, so they will probe more restrictions and barriers. So we do know that the diffusion coefficient is not constant. It depends on time. And this is another way of probing the non-Gaussian properties of your diffusion. And for instance, if you vary the diffusion time from 1 millisecond to 1,000 milliseconds, you would vary from about 1 micron to 50 microns. So this would be the different length scales you can probe. I'm showing here the example of brain white matter. So the diffusion dependence in brain white matter has been shown as early as in, I think, the 90s. But this is shown here for major white matter bundles. So we are going from about 50 to 500 or 600 milliseconds. And what you can see is that the diffusion coefficient along the fibers, the axial diffusivity, clearly decreases with time, as well as the radial diffusivity. But the most pronounced here is the axial diffusivity. And this is quite interesting, because what does this imply? Well, this implies that exons are not really cylinders. There's something structural along the exons hindering the diffusion. And how can we understand this? Well, for that we can look at EM microscopy. This is the GNU mouse corpus callosum. And if you would focus on, for instance, one exon, you can actually see that those exons vary in diameter along the z-axis. So this kind of implies that exons are indeed not straight cylinders, and there may be many effects that can explain this time dependence. It may be undulation, it may be beats, it may be dispersion. So all these effects should be studied as well. And so how did we explain here this effect? So we found this formula for 1D time dependence. We know it should go down as 1 over square root of time. So if you would plot it as 1 over square root of time, you expect a straight line, which kind of seems to be true. And from this, you can also extract a length scale, which is between 3 to 7 microns and 3 to 5 microns. And interestingly, if you look into the literature, you can find the distance between varicosities is indeed on this order. You can see it varying from 3 to about 7 microns. And so this would be another way of how you can use time-dependent diffusion to probe varicosities, which may be changing in ischemia or Alzheimer and so on. So in summary, I hope you can see that by biophysical modeling, you could become sensitive to the underlying pathology with diffusion MRI. The diffusion can be varied by both measuring the diffusion gradient as well as the diffusion time. Most of the work today has been done by varying the diffusion gradient, Q. On the one hand, you have signal representations such as DTI, DKI, Q-ball. They are very sensitive, so we should not disregard them. Remember the example of stroke. You can see the huge drop in the ADC. But they are not by design specific to microstructure. That's why we try to do biophysical modeling. Biophysical modeling is hard. There's a lot of simplifying model assumptions that need to be further validated. And finally, I show that you can also vary the diffusion time, and this will give you another way of probing the microstructure directly. And then if you're interested in biophysical modeling, there's this nice review paper from Jason Lurch that just came out in Nature Neuroscience. If you're really excited about modeling, there's a diffusion MRI modeling paper that we actually put together and is already available on arXiv. You can have a look at the end. There's like 10 open questions that still need to be further addressed. And then I already explained the degeneracy. There's another few things. First of all, I only spoke about standard Statistical tenor monopolar gradients. Jennifer also already mentioned it, but there's other diffusion weightings. There's double PFG, double pulse field gradients, and there's more recently there's been proposed to free gradient waveforms, Q trajectory imaging, by the group from Marcus Nilsson and C.F. Westin. They have the potential of becoming more specific, to have more information to probe the microstructure. Then there's still a lot of open questions. I didn't go into the effect of compartmental T1 and T2 relaxation, which may alter your diffusion coefficients. And then there's also the gray matter. Typically, the gray matter has been, the dendrites and the axons have been collectively called the dendrites. However, it's not clear whether dendrites really are impermeable at the time scale that we look with diffusion MRI. So there's still a lot of open questions. Maybe the time-dependent diffusion MRI could help for the gray matter as well. So with that, I'd like to finish, and thank you all for your attention.